Hi students, briefly to continue about our fits, these would be the list of the fits, and per those tables that we were talking about here, this would be the ASME B4.1 and 4.2. There are 9 classes of RC fits, there is 11 classes of LC fits, there are 6 classes of LT fits, 3 classes of location fits, interference fits, and then 5 classes of force fits. Yeah, calculating these size limits, that's what I said we're not going to be doing in this class. We're just talking about this. But you need to consider the functions of the parts being considered, to select what fit you need. And the descriptions of the general applications are provided. Then you need to determine the class of fits and determine what the tolerance values are. And remember that the tolerance is proportional to the size of the features. So a RC1 fit is different if your shaft is 1 inch versus your shaft being 5 inches. So the fit is proportional to the size of the feature. Okay, let's move on from there. Let's talk about maximum material condition. We're going to be talking about maximum material condition a lot in this class. So the maximum material condition exists when a dimension feature of size is produced at the limit of the size tolerance. Okay, so you need to think about these things differently if it's an inside feature like a hole versus an outside feature like a shaft. For the hole, the MMC is the hole when it's at its smallest size. Okay, when the smallest hole is going to have the most material. Okay, so the MMC condition is when the hole is its smallest. That is allowed by tolerance. For a shaft, the maximum material condition is when the shaft is at its largest diameter. So this is a shaft right here, and the dimension is 750 thousandths plus or minus 5. So therefore the MMC on there is 755 thousandths. You add the tolerance to that to get the maximum material value. In this case, it's a hole, it's an inside feature. The maximum material value, you would be subtracting the applicable part tolerance. Okay, so that's just an introduction. We're going to be talking about that term a lot, but that's a very important thing to distinguish, is that MMC for a hole is the smallest hole and MMC for a shaft is the largest shaft. So let's talk about rule 1 of GD&T. Perfect form is required at maximum material condition. Okay, when we're using GD&T, we're going to have form tolerances, and we're going to have these other kind of tolerances. Okay, so what we're saying is when you're at your maximum material condition, the part has to be of perfect form. So perfect form is required at MMC. Any dimensional regular features of size must have perfect form at the maximum material condition. And what this will also do, it will establish the perfect form boundary at maximum material condition. Okay, so variations of features and size, variations on size of this feature of size must not violate the boundary. And the feature may not be perfect at the least material condition. Okay, so when you make your part at the maximum, you need to make sure that the form is perfect. But when you're going towards the LMC, you got more leeway in terms of form. And this is a term that's going to keep coming up, and we're going to beat the hell out of this thing, as we go along in this course. We're going to talk about perfect form and MMC, but we're just introducing it here. Here's some examples of Rule 1. Here is our drawing requirement. We've got an inch plus or minus 10 thousandths. Okay, and if we produce that part at MMC, it would be an inch and 10 thousandths. And when we do that, the cylinder must be perfect in form. Okay, so let's take a look here. If we made it at 990 thousandths, our perfect form envelope here is at 1 inch and 10 thousandths, and so that's our perfect form boundary. And you can see that our 990, we have a little bit more leeway to vary at that point. Okay, because we've got more room to work with. And when we start talking about MMC and GD&T, what we're really doing is talking about making parts that fit at the next level assembly. Okay, so if we didn't have perfect form at MMC, we would violate these boundaries, and chances are we could not get that pin into the hole that we needed to at the next level assembly. So typically when we dimension parts and use MMC modifiers, it's to assure fit in GD&T. Okay, here's another one. You got a part produced at LMC, it's just 990. So we can have that thing bowed and it would still fit. Okay, so feature variations within the MMC envelope are permitted. Okay, so that's what we're talking about. As this dimension here approaches this upper limit value, we don't have any tolerance on the form, because if we did, our part would not fit. Okay, so that is rule 1, very important. Perfect form is required at MMC. Okay, so let's talk about a couple exceptions to rule 1. Rule 1 does not necessarily apply to stock shapes and sizes. Other exceptions may be invoked by applying tolerances or modifiers. So geometric form tolerances to control straightness or flatness of the derived center. Okay, that's the other way to do it. Independency symbol to a size dimension, and geometric tolerances with a free state modifier. Let's talk about those. Okay, let's talk about interrelationships here first. Okay, so rule number 1 does not require perfect relationships between features. It's just talking about perfect form at MMC. They only force imperfect relationships if the part function requires a high level of control. Okay, so let's look at this one here. We have a drawing requirement here that's size and size, and we also have this angle here with the tolerance. And if we look at what that means in terms of producing an acceptable part, look at this dimension here is at its MMC, and this dimension here is at its MMC as well. Okay, and then we have this tolerance here. Okay, but when we're at MMC, we have to have perfect form at MMC. Okay, in which case it forces us to assure that if the part's acceptable, that these two sides here are parallel, because they are at the MMC limits. So perfect form is required at MMC. Therefore, these two sides must be perfectly parallel to meet rule 1. Okay, and likewise, these two sides have to be parallel to each other to meet rule 1 as well. Okay, this is an introduction to rule 1. Perfect form is required at MMC. Okay, now that being said, let's introduce number 2. Number 2 says, regardless of feature size, RFS is going to be applicable for all tolerances unless otherwise specified. Okay, so what we're saying here is the regardless of feature size modifier is assumed if we don't specify any other modifiers. So if we want our tolerances to apply at MMC, for instance, we have to use a modifier, because if we don't use a modifier, RFS is applicable. And then regardless of material boundaries, we talked about this before, when the MMC modifier appears in a datum reference, it's called RMB. And so when we're not using the maximum material boundary, the MMB, we are going to be defaulting to this RMB for all datum feature references unless otherwise specified. So let's talk about that a little bit more here. In this feature control frame, we do not use any modifiers. Therefore, we assume per rule 2 that that this tolerance here applies at RFS, and that all of these datum references here apply at regardless of material boundary. Okay, now if our part can live with the MMC modifiers, we need to specify those explicitly here, because without the explicit use of the material modifiers, RFS or RMB is always assumed per rule 2. A couple more slides here. Dimensions for industry. Datums and tolerances establish allow variation and required relationships. Size and location specifications, primary requirement for dimensioning and tolerancing models, and orthographic views. We apply dimensions and tolerances with considerations to the part's use. We've talked about this before in this class, where you always have to be mindful of how the part is used, and you have to calculate what your tolerances are, or else you won't get what you need. Revisions may occur after product definition is released, and we need to be careful with those calculations and stuff, because we want to limit the amount of changes that we make in a part that's in production. Now, interchangeability, I mean, that is the whole thing. That is the whole key. That's why we use GD&T, because we can buy our parts all over the world. And what would happen would be we would bring those parts and they'll fit and work in our assembly if everybody understands GDT and all those parts are made to those requirements. So interchangeability is an important fact. Machine capabilities. The point here with this slide is that the tolerances that are achievable is determined by your manufacturing processes and the machines that are used to create those features. This movie was a little bit long. I'm going to have to end it here, and this concludes lesson on chapter 4.